Today we're going to talk about the master theorem. We'll describe what the master theorem is and how to use it, and we'll reserve to the next video a proof. So we've had many occasions where we have had to write a recurrence relation for a divide and conquer problem. This is an example of one for binary search. We break a problem down into a problem half as big, and we do a constant amount of work at each level, and this gives us a solution, t of n equals big O of log n. The problem is, for each one of these, we have to create a recurrence tree, figure out how much work is done at each level, sum up that work. That's a lot to do to solve each recurrence relation. Here's an example that we used for the polynomial multiplication. So we broke a problem into 4 subproblems, each half the size, and did a linear amount of work. And the solution was t of n equals big O of n squared. When we had the more efficient algorithm, where we had only 3 subproblems instead of 4, we then got a solution of big O of n to the log base 2 of 3. Sometimes we break a problem into only 2 subproblems, and there the solution's big O of n log n. So wouldn't it be nice if there was a way that we just had a formula to tell us what the solution is, rather than having to create this recurrence tree each time? And that's what the master theorem basically does. So the master theorem says, if you have a recurrence relation, t of n equals a, some constant, times t of the ceiling of n divided by b, plus a polynomial in n with degree d. And that ceiling, by the way, could just as well be a floor or not be there at all if n were a power of b. In any case, the a is a constant greater than 0, b is greater than 1 because we want to actually make sure the problem size gets smaller, and d is greater than or equal to 0. Well, in that case, we have a solution for t of n. There are 3 subcases. Case number 1, and all these cases depend on the relationship between d, a, and b. In particular, is d greater than log base b of a? If so, the solution is just this polynomial in n, big O of n to the d. If d is exactly equal log base b of a, then the solution is big O of n to the d with an extra factor of log n. And finally, if d is less than log base b of a, then the solution is big O of n to the log base b of a. So let's look at some applications of this theorem. So here's one where we go back to the polynomial multiplication. Here a is 4, b is 2, and d is 1, because big O of n is just big O of n to the 1. And we look at the relationship between d, which is 1, and log base b of a, which is log base 2 of 4, or 2. Well, clearly d is less than log base b of a, so we're in case 3. Therefore, t of n equals big O of n to the log base b of a, or just big O of n squared. If now we change the 4 to a 3, a is 3, b is 2, d is 1, now d is still less than log base b of a, because log base 2 of 3 is greater than 1. And so, again, we're in case 3. t of n equals big O of n to the log base b of a, which equals big O of n to the log base 2 of 3. If we reduce the 3 down to a 2, what happens? Well, here, a is 2, b is 2, d is 1. Log base b of a is log base 2 of 2, which is just 1. So now d is equal log base b of a. We're in case 2 now. And so t of n equals big O of n log n. And now this shows an example also of case 2. So this is the binary search example. A is 1, b is 2, d is 0. Well, the log base 2 of 1, log base b of a, is equal to 0. So d is equal log base b of a. We're in case 2. T of n equals big O of n to the d log n, which is in the 0 log n, which is just big O of log n. And a final example where we're actually in case 1. So here, a is 2, b is 2, and d is 2. So log base b of a is log base 2 of 2, which is 1. So d is now greater than log base b of a. We're now in case 1. T of n equals big O of n to the d, which is big O of n squared. So what we've seen now is that we have this master theorem that allows us, for most recurrences having to do with divide and conquer, which fit into this general formula, allows us to easily figure out which case we are based on the relationships between a, b, and d, and then figure out the result quite quickly. In our next video, we'll look at a proof of why the master theorem works.